Hi, so this is Mr. Max again with vectors in 2 and 3 dimensions. Good. So there's quite a lot of things that I would want you to have a look at, and in order for you to perhaps focus on whenever you are dealing with these type of questions. All right. So there is quite a number of things. So you need to do a quick revision maybe on unit vectors, coordinates in 3 dimensions, and vectors in 3 dimensions. We're going to look at that. And then also, in this particular one, we're going to work with those three-dimensional vectors. We're going to find specific unit vectors. We're going to represent the stuff geometrically, the relationship in terms of vectors. And then we're going to interpret such vectors. All right, so please have a look at your work on Pythagoras' theorem. It's going to come in handy, especially when we are finding the distance. All right. Good. So translation, let's quickly look at what translation is. Well, first of all, you know that this is a a sliding movement of an object. So if I have triangle ABC, as you can see here, and you want to translate it, the movement from B to C is written in vector notation, capital letter B, C with an arrow on top of it. Okay, so you can say, well, you're going -1 in the negative direction of X, and then you go 2 values up. All right, as a vector, it can be written as -1, 2. All right, and this is called a column vector. Now, there are many ways that you can represent vectors, but this is going to be the basis at which we are working from. Right, so when you look at these two here, you have got a vector. What it is a quantity which has direction and size. The length of a line shows its magnitude, and the arrowhead shows the direction. So, for example, this is F to G, all right, D to E. And you can also see that these two vectors have basically the same displacement, the same vector, all right. From F to G is the same displacement as you would go from D to E, all right. So, if you look at points F to D, you can see that F and D have been displaced to G and to E respectively. So the arrow FG and the arrow DE represents the same displacement, the same vector. Right, so a displacement is written in that form, and also we call the starting point of the letters the initial point, and the ending point is called the ending point, terminal point, okay? Right, so if you look at vectors, FG is different from GF because it's from where you start from. In order for you to make them equal, you have to put that minus there. Right, so let's look at another way that you can represent vectors where you have got that squiggly letter, small d there, like a circumflex something there, like a D. So it can also be represented by, small letters with lines underneath them. But then you know that they are still talking about the same vector FG. When you use this form, don't leave out the arrow, otherwise you will now be talking about a line segment, not a vector. So when you use capital letters, make sure that you put an arrow on top. Small letters, make sure that since you can't do it in bold form, you probably have to underline that D, okay, by putting a little line under it. Okay, so we have got position vectors. Now, what are these? Well, these are vectors that are starting from the origin. That's as simple as that. OA, OB, OC, they are position vectors. Now, if you look at vector OA and compare its coordinate is 1, 1. Look at vector OB, which is 2, 1. Its coordinate point will be 2, 1. Something very interesting. Look at vector OC. Its coordinate is 1, 3. So very important that you understand, because they start from the origin, they are tied to the origin. Because sometimes you will be expected to write things in position vector form or in coordinate form, or go back from coordinate form to position vector form. Okay, right. So you have got exactly in the diagram, you have OA, OB, and OC. Okay, as you can see here. And if you represent them by small letter, OC will be represented as small letter, which is vector C. OA will be vector A, small letter, so you will be drawing a line under that. OB, small letter B, can also be written like that. Okay, they may be written in terms of the position, vectors OA, vectors OB, as you can see. Now, this is a very important slide here. And I will suggest that maybe you pay a little bit of attention to the slide. So you can see that if you were the displacement vector AB, it's like you're going from A to B. So you're going A to O and then O to B. It's very important that you understand that. Okay, so I'm looking for AB. So going from A to B is the same as going AO plus OB. Well, we're going to talk more about that in terms of how you write that. But AO then is not a position vector, so you have to write that as a position vector. Okay, so you have to put a minus in there. So if you go AB, then you must have OA and minus D because you're going against vector A. Can you see that? Against vector AO or OA in that regard. Okay, right. So in simple terms, if you have AB, vector AB is equal to the second point, the position vector of the second point, minus the position vector of the first point. It's very important that you get that concept in. So if you were to write this once quickly, EF, yes, it will be the same as EO and OF. You have to bring in that third point to do your position vector. But remember, this is not a position vector, so very straightforward and very easy indeed. If you had to write that down, then you will probably realize that it's the position vector of the second point of the second point minus the position vector of the second point. That is going to allow you to get to that. Okay, so how would you do this one? So of course this one would become nothing but the position vector of the second point, which is OH, minus the position vector of the first point, which is OG. The same applies here. Position vector of the second point minus position vector of the first point. Okay, so all of that should give you the displacements. All right, I hope we would arrive at the same answer as I arrived at them there. So you just take away that, and then you have an indication and a clear way of how that particular question is supposed to be done. Right, so magnitude of a vector. So when we talk about magnitude of a vector, there's obviously a few things we look at. Magnitude, the size of a vector, and addition and subtraction of vectors. So magnitude of vector OB is the length of the line OB. So please don't take a ruler and work it out. Okay, you have to use Pythagoras' theorem because these things you will see you can represent them on a Cartesian coordinate system. Okay, right. So and the modulus of the vector can be written with the two bars and a little arrow on top, or if you're using small letters, then you must put a little line underneath. So if I was now writing this out, so the modulus, so let me just bring in my pen. So the modulus will be written like that with a little line there, because you can't make this bold, right? Or the modulus of that, or the modulus of that. Okay, I hope you get that idea. All right, so in order for us to find the magnitude, to use Pythagoras' theorem. Okay, so Pythagoras' theorem then give us that indication. So if you have vector OB, as you know in our previous diagram, you just have to go square root of 2 plus square root of 1. So basically this is what it is. So the distance from O to B is that distance squared plus the distance squared. Take that as the root, and that gives you the answer. All right, so it doesn't matter if this distance is negative, anything squared becomes positive anyway. You can add and subtract vectors, no problem. The vector AB is equal to AC plus CB. This is quite an important concept because I had to bring in a third point, and I'll explain this also as we get vector AB. This is the same as going from A to C and C to B. You see, it's like your A and your B are your starting and ending points respectively, and the C is the one in the middle. It's like they are sort of canceling out each other there. Okay, and then you can actually then find that. So this concept is going to be quite useful to what I'm going to do on later occasions. Right, so here we've got addition of vectors. So let us see how we are going to deal with that. So if you look at your addition, so you have got, let's say, vector OB, which is 2, 1. So vector OB is 2, 1, and we are going to add OA plus AB. All right. So if you add those vectors, so OA plus AB, all right, which OA is 1, 1, and AB is nothing but um, AB from A to B. You can see it's just X direction and nothing up or down. So you add the elements together, and if you add the elements together, then the answer that is called the resultant vector. All right. So you start at the same point, end at the same point, then you get the resultant vector. Right. We define vector BO as being the same as vector OB but with a negative in front of it in order for us to be able to determine. Okay, so we also look at things called multiplication of vector by a scalar quantity. So if you have vector OP and you say vector OP is equal to twice vector OC, you can see that in terms of the line segment is twice as long as OC. All right, so twice as long as that. So basically you can see that that 2 is a sort of a scalar multiple. Okay, and vectors that are equal, well, they have X and Y directions, components are equal no matter where they are free, they don't have to necessarily start from the origin, right? CD, if you look at the X component, is 2 and 1 up, and that is the same with vector EF and vector AB. Okay, so we say that they are all equal. Parallel vectors, now this is very important that you understand this particular concept. With parallel vectors, then I have to rush through, there's a lot of slides, about 55 slides, and you can see I'm at slide 11. If you look at two vectors, we say vectors A and B are parallel if one is a scalar multiple of the other. Okay, so vector A is equal to, if you look at that, lambda times B, if that is positive, if your scalar quantity is positive, the vectors are parallel and in the same direction. It's very important that you understand that. If the scalar quantity is positive, parallel, same direction, we call them like vectors. So like parallel vectors, like for example, vector U and vector V here, same direction, okay, and the scalar quantity is positive. But if your scalar quantity is negative, the vectors are still parallel, but they go in the opposite direction. So unlike vectors are also parallel, the same like vectors. So the difference between your like vectors and your unlike vectors is that like vectors, scalar quantity is positive, okay, and they are parallel and go in the same direction. But unlike parallel vectors, the scalar quantity is negative. So therefore means the vectors will go in the opposite directions, but they are still parallel. Very important that you understand that particular thing. Well, the zero vector, you can have a concept, a clear indication of the zero vector, right? So consider OB and DC. When you look at OB and DC, so O to B will be 2, 1, and D to C will be minus 1, minus 2. So basically, if you add them, you get 0. So zero vector is where a vector that its resultant is just going to be 0, 0. Okay, both its X, Y component are equal to 0. If it's a 3D vectors, then both its X, Y, and Z component will be 0. Right, so we have got an exercise here that you can have a look at. Given that OA is equal to 3, 4, vector OA, vector OB is equal to 2, 3, give AO and AB as column vectors. And this is very important. You can perhaps even stop that. So AO, remember AO is not a column vector yet, or it's not starting from the origin, okay? Um, so we have to make it start from the origin in order for it to be a position vector. So AO is the same as minus, so you're going to put a minus in front of that. Okay, very important. There is a reason for that because AB is equal to second vector, second displacement point, or the second position vector point minus the first position vector point. Hence, I had to do that swapping thing in the beginning. Okay, so that's going to give me vector AB is nothing but -1, -1, while vector AO is nothing but -3, -4 when you write it in terms the other way around, because A is given as OA. So OA is 3, 4. So AO means there's a minus now. It's going to be negative, whatever that vector is. Right, so in this particular case, the diagram shows vector A and vector B. And if you look at it, you have got column vector. So from B, you're going 4 places to the right. Make sure you understand your scale, and 1 place down. So that's how you write it. Okay, so vector A is nothing but 1, 2, and then you edit it twice, whatever that is. So you can actually work that out. All right, and then you go ahead and you get to your final answer. Okay, and your final answer will just be adding the x components together and the y components together. Should get 90 as a final answer there. Right, here you have got 3a. It says a is the point 3 comma negative 5 and b is the point 4 comma negative 7. You see, these are given as coordinates. So first we have to write them in terms of displacement vectors. Same component, just written in vector form. The same with OB. So if you have AB, it will have to be OB minus OA. So you needed to write in that form first, and then you simplify and give your answer as 1, negative 2. Okay, so here you're given as coordinates, and it's very important that you understand the coordinates can be written in vector form, considering the position starting from the origin. So here you have got position vectors of C and D, 2, negative 1, and negative 4, 2 respectively. So we want 2 times CD. So basically you have to find CD, and then you take that answer and you multiply it by 2. That's scalar multiple. So again, you have to do the same thing. All right. So OCD will then be OD minus OC, remember, second position vector point minus first position vector point. All right. And once you can do that, you should get to an answer. Well, so now we know what CD is equal to. Okay, now you can just double that, just multiply that by 2. All right, which give you negative 12, 6 as a final answer. Right, so here you have got another vector E and vector F, and then you have to find the following vectors. Well, half of E, you take each component in E, you half it, and when you do the second one, you just take vector E, subtract vector F, subtract the components from each other, and E plus 2F means you take vector E plus twice vector F. Okay, you should therefore definitely get to the same answers as I did. Okay, right? You don't have to show most of the steps, but here, step by step, will allow you to be able to solve the questions. Okay, right. So let's look at this particular diagram. So you have got P is vector OP, Q is vector OQ. You see the arrow indicates. Now you have to write down PQ. So how do you go from P to Q? Well, you go PO plus OQ. Okay, so we're going against P plus Q, which you can just simplify as Q minus P. So it's basically how do you go from one point to another in order for you to arrive at that destination. This would be the shortcut version, or you go along this route and up there. That's how you go from P to Q. Okay, so you start at P, you have to end at Q, but they have to go from P to O plus O to Q. A lot of other students, they can tend to make this before they write in terms of the letters in which the particular vectors are given. Right, so here they ask you to calculate the values of A and B. So you have got 2A plus B is equal to A, and A minus B is equal to that component there. So here you just equate 2A plus B is equal to A, and you can go ahead and solve that. Well, it will give you A is equal to minus B. That is the solution to that first equation. The second one will be A minus B is equal to 3 plus B. Right, so we know what A is, okay? So we know that, first of all, I move all the terms so I can have the number on the side. Now I know what A is minus B. So if I simplify this particular equation, I get A minus 2B is equal to 3. So everywhere where I have an A, I can substitute it with minus B. Okay, so that means I substitute minus B for A, and then I find the value of B, which is negative 1. Once I have the value of B, and I can find the value of A. So if B is negative 1, then A should be positive 1, because it's going to be not negative times whatever the value of B is. Okay, right. So unit vectors, this is very important that we talk about what unit vectors are. We're going to work with important idea that you also have come across in your work on two-dimensional vectors. This base vectors, also known as unit vectors. This is a vector where that is a magnitude of 1. All right. So if you look at this example here, you've got 1, 0 and 0, 1. So this vector is very easy for you to see that the magnitude of this vector, if you have to use Pythagoras' theorem, you get 1. But it's not so easy to find this one here. So this one here needs more work, 3, 5, and 4, 5. So we're going to spend quite some time looking at that on a later basis. Right, so you have got your vectors. If you look at your vector I10, which is a unit vector in the positive x direction, so that is like one value to the right, okay, but it doesn't go up or down, so this would represent those. And we use the letters I and j in two-dimensional vectors to represent our base vectors or our unit vectors. All right, so I would be the vector 1, 0, and j would be the vector 0, 1. Okay, so if you know your alphabet, you know that j comes after I. All right, the same of x comes before y, so it's very easy and interesting to remember that. Okay, unit vectors, let's continue further with that. So let's say p is the point 2, 1. So that is the coordinate point. So the position vector would be of OP would be 2, 1. And we could write OP as well. This is just a long way of arriving at what that particular concept is. You'll understand that. So if I take out a 2, right, and you're gonna have 0, 1, because it's like the same as twice the position vector, which is 1, 0, plus 1 time the one under. All right, well, that gives you 2i plus 1j, or 2i plus j. So in short, all that you need to do is just look at your components. 3 on top, that means 3i plus 4j. That's how you write it if you want to write it in base vector form. Negative 10, 6.5 can become negative 10i plus 6.5j. So if the question in the exam asks you to give your answers as base vectors, then you give your answers as base vectors. If the question asks you to give the answers as a vector in column vector, then you give it in column vector form. All right. So here I have got base vectors, and then you have to write in column vector form, so it becomes 7, negative 5. Okay, so 8i, what does that mean? Well, there's no j component, so j will be 0. That's how you write it. The same, if I give you a j value, that means I is not there, so 0, negative 1. Right, so the coordinates in 3 dimensions, very important. So we use the x and y coordinates to give us the position of a point in 2 dimensions. So like, for example, point 2, this point P will be the point 2, 1. So this is a coordinate pair. It's very easy. But if we imagine this two-dimensional grid, let's say it goes now flat. So there's going to be another axis that comes up now. So it's very difficult kind of to represent this on a two-dimensional flat surface like this. But you see where my point x, y is now. So the point is now there. So it hasn't moved up or anything. So to describe the points, we have to bring in a third dimension or third point, which is the height, and we call that the z or the z coordinate. Right, so you have got many ways that this can be represented. Positive for x there, and as you go down for z, you come negative. As you come, I don't know, towards yourself, to say you're drawing this, and then towards yourself, the y is negative, and x, when you go to the left, it becomes negative. You can look at it that way, okay? So these are rectangular Cartesian axes, and they're always right angle to each other. So we always have them as x, y, z. So if I were to bring in a point, P is a point 4 units directly above K. So if you have to represent that, you see this point K is here. In fact, we can also write the coordinates of K down. So it will be 3 in the x direction, 2 in the y direction, but doesn't go up. So that point will be 3, 2, 0. And point P will be 3, 2, 4, because it's 4 units above K. Okay, so 3, 2, 4. And the K would be 3, 2, 0. For example, if you had to look at this particular coordinate system. Right, so we always write them in that form. Okay. Right, so the axis may be rotated. Again, this is a kind of a bit tricky. If you rotate it, you can see somehow I've rotated, and now it looks like the axis on this side. And again, if you rotate in the other way, so it's you playing around, but we'll mostly use this pattern here. All right, so let's look at example. Here are two examples showing you how to use the coordinates of 3 dimensions or in 3 dimensions. So you've got the rectangular prism. You've got the dimensions as given, and the diagram shows it. So we need to find each vertex and write them in terms of the coordinates. So I drew it here again so that you can see how the box will be. So if you look at the diagram or the picture here, it gives you quite an understanding of what's going on. So A to O is 1 unit, O to B is 3 units, and BC is 2 units. Okay, so we have to give the coordinates as well the corners. Right, so let's bring that. So first this is 0, 0, 0. There's nothing much you can do there. A then will be 0 in the x direction, 0 in the y direction, just one up. Okay, so B goes 3 in the x direction, doesn't go anywhere in the y direction, so it's 3, 0. Doesn't even go up, so it's 3, 0, 0. Okay, and C, well, you go 3 in the x direction, 2 in the y direction, but doesn't go up, so it's 3, 2, 0. So we say C is 3 along the x, 2 along the y, and nothing up the z. Okay, right. D, well, again 3, 2, and then obviously 1 unit up. Okay, E, well, E is there, nothing along the x, 2 along the E, and nothing up the z. So it's 0, 2, 0, 0, 2, 0. F, well, F is again nothing along the x, all right, but 2 along the y, and also F is nothing, or it's 1. See where F is up there, so it's 1 unit above the z coordinate. So 0, 2, 1. So I'll let you play around and find G for a minute. I hope you arrive at the same answer. G is 3, 0, 1. Now there's something very interesting. Can you work out what the coordinates of the midpoint of GD would be? What will the midpoint of GD be? How do you think you'll calculate? Well, you have G, you have D. Just take each one of those coordinates, add them, and divide by 2. Okay? Add each and divide by 2. So you should get 3 plus 3 is 6, half of 6 is 3. 0 plus 2 is 2, half of that is 1. 1 plus 1 is 2, half of that is 1. So that's how you'll find, for example, the midpoint of coordinate GD if I was to ask that. All right, here we have a totally different one. Here we also have to find the coordinates. Maybe it's a wedge, and it says its base is the rectangle ABCD in the XY plane, as you can see under there. So it says that the face BCEF, this one here, is parallel to XY plane, and something is parallel to the XY plane. It means obviously it's parallel. And then the coordinates of A is given as 0, 2, 0. The coordinates of E up there is given as 6, 5, 5. So how would you find the coordinates of B? Right, so B, you mean to have to go along somewhere in the x direction, so that has to be 6, and then 2, but nothing up there. All right, so C again, you have to find that by saying, okay, C will be 2, this direction here, along the x, because along the x it has to be 6. Along the y, now you must be careful of C, you see, because B along the y is 2. So C, you understand, the C is very important. In order for you to find the distance of B to C, okay, that means you have to look at your y's. So that's like 5 minus 2, so that's 3 units there. So you have to be a bit careful there. So it's 6 for that point, and then that point there, the y value is 5, because it's 2 here, okay, and it's 5 there. So you have to say 2 plus 3 in order to give you that value there. So it's basically the same as E, but now it is not going up there. And E, yes, E we have already. What about F? I'll let you ponder a bit and see if you can determine F. So F, how many units along the X? That's 6. How many units along the Y? That's 2. And then obviously 5 up. Okay. Right, so that's the picture representation of how it would be looking if you were to play around with that. Okay, so we have got another question here. It shows a unit cube along. So cube means all of the distances are basically 1, 1, 1, 1. okay, everywhere. So how do you write down the coordinates of all the 8 corners? Well, pause the video and then you can actually do that. And then you write down the coordinates of the midpoint of AF, remember I said, and write down the coordinates of the point which lies at the very center of the cube, somewhere in there, right in the beginning. So it'll be a lot of halves there. All right, so I hope you get to the same points as this for all the points of the cube. This is what you have. And then B, the coordinate midpoint of AF, so whatever A is and F is, just add X and Y and the Z's together, or the Z points, and divide that by 2. And you should be able to get this answer here, 1, comma, a half, comma, 1. Coordinates of point at which which lies at the very center of the cube. Well, that's very interesting. It's just going to be half everywhere, half to the X direction, half in the Y direction, half in the Z direction. Right, we have another square base pyramid. As you can see, you have got 2 units across here. And they say the size of it's square, right? So AB is also going to be 2 units, okay? And the vertex V is 3 units up, so that will be 3 units up. So what are the coordinates? A will be 0, 0. Well, now you go 2, so it's 2, 0, 0. And C would be 2, 2, 0. You agree? And D would be 0, 2, 0. You agree? Now, what will V be? So V is very interesting. So let me just bring in what I have so far with my points. So V will be the point 1, 1, 3. How do you get that? Because it has to be half of whatever the distance is here and half of the distance of y. And that will be the center somewhere there. So it has to be half, half, half of 2, half of 2. So it's 1, 1. And then 3 up, as you are told, 3 units above the center of the base. That is a square. Right, do you have another figure here? Now that slope that you see here is 45 degrees, an xy plane, and you have to write the coordinates of each of its vertices. Now very interesting, I'll let you pause and maybe you can play around. Right, so A is very easy, it's just 0, 0, 0. B, obviously you go 3 in the x direction, but you're not going up, nor are you going, to the y, in the y direction. So C would be 3 here, 5 all the way up to there, but doesn't go up. D, wherever it is, doesn't go in the x direction, so that's 0, but 5 there, and it doesn't go up. So the next one is E. Well, in order, before I can do the next one, okay, there's something that I want to bring in. If you look at triangle BGT, so if it's 45 degrees here, then that angle there is also 45 degrees. So you don't have to use this tangent stuff in order for you to be able to determine that that distance will be 2 units, because this is an isosceles right angle triangle. Okay, so you do get it, right, that this particular part here, this angle is 45 degrees, that angle there should also be 45 degrees. So that means that should also be 2 units up there. All right, and then you have it. Okay, so why is that important? Well, it allows us to solve our next problem, E, in order to find how high up E should be. All right, so E would be 3 units in this way, 5 units in that direction, which corresponds to what you have on that side, and 2 units up. So F, again, 0 in the x direction, 5 in that direction for y, and 2 up. No problem. So it's very easy for us to realize that, wait, but that is 2 up there as well. All right. And what do we have? G would be 3 up here, and then a little 2 as you can see, and obviously 2 as you can see there. And H is 0 in the x direction, right? See where H is. But remember, H is also exactly, how can I put it? If I had to, it's just a little skew, right? But that will be 2 units up there. Okay, because the height is 2. And then obviously 2 units across, same like G. Okay, so you have got a cube of size 2 units, so it's 2, 2, 2 everywhere. You have supposed to write down the coordinates of all 8 vertices. So this is very interesting. So you see where the center is. The origin for that is parallel to the edges. So I drew it something like that. two sides of the cube are each 2 units. So from the origin to any face will be 1 unit. Okay, so it will be 1 unit, 1 unit. So A will be like 1, 1, because our A will be somewhere here. Our B now is going down, right? But remember, X is positive, but then your Y is negative because it actually comes, as I said, it's towards you, and it is going down the Z parallel, so it has to be negative. The same with C. C has, now you have to be a bit careful where C is, just the way you see it. C is actually positive in the Y, positive in the X also, but it's under, so it's underneath, so it's basically on that part of the quadrant. Then D, well, D is a point that is going to be negative for X, but positive for Y, because it's sort of on the other side, right, of the quadrant. It's right, that cube is right in the middle. All right, you have to imagine this in 3 dimension. Okay, then H or E will be negative 1, comma negative 1, comma 1, and F will be 1, comma negative 1, 1. G, well, G will be somewhere around here, so everything of G will be negative, and everything of H except the X direction will be negative, will be positive. So X is negative, and then 1, 1 for the other values. Well, it's kind of, trial and error until you figure it out. So that's how that particular thing look like. So I just brought in a few for you to have an idea. It's very difficult, as I said, to represent this on a 3-dimensional surface, but you can always look at it like this. Might help you in a little bit. Okay, right. So vectors in 3 dimensions must have 3 components. You look at Q. Q is 2 units, and then 1 unit here, and then obviously 4 units up. It's very difficult, but the way you go 2 units there, 1 unit here, and 4 units up there. Okay, and it can be written as a position vector as 2, 1, 4. So it's 2, 1, 4. If you write it as a position vector, starting obviously from the origin, this concept is the same. So when you are given a coordinate triplet, as you are given 2, 1, 4, in vector form, it just becomes 2, 1, 4. Okay. So unit vectors in 3 dimensions. So we had unit vectors in 2 dimensions. So in 3 dimensions is I we know is 1, 0, and j is 0, 1. So z, now we have to bring in the third one. So we're going to use k. So the letter k. All right. So I would be, because it's 3. So 1, 0, 0. J is the alphabet. Okay, 0, 1, 0. And then k would be 0, 0, 1. So that's basically how you should remember them in terms of base unit or unit vectors. And you should also know when you are adding and subtracting and multiplying a scalar quantity, you follow the same logic as you would have followed when you're dealing with 2 dimensions. Okay. So when we looked at other point that we had, so the point was position vector was 2, 1, 4. Well, and as a vector is 2, 1, 4. And now as a base vector or unit vector is 2i plus j plus 4k, 1j plus 4k. Good. Negative coordinates, a little bit tricky, but you should be able to see the negative sides in the 3D coordinate axis. So, for example, try to imagine the xy plane as a floor. So the points of negative z coordinates lie under the floor. Okay. So S is basically a point that is under the floor. So you go 2 units in the x direction, or it's 2 units if you look at where x is, because it's difficult because it's on the other side. Okay, so it's under, right? You see where it is. So you go 2 units in the x, then you go, what is that, 4 units in the y, and then you go under. That's how that particular point looks like. So the distance from O to A, absolute distance there is 2 units. Distance from A to B is 4 units. The distance from B to S is 5 units. All right, the modulus of that. All right, so how do we add vectors? So PQ, and we know that adding vectors PQ is the same as saying P. So we have P to Q is the same as saying O to P plus O to Q. All right, so O to P. So we have to go all against that, right? We know that from PQ we have to take the second position vector point minus the first one, right? But then what is the OQ? O to Q would be 2, 1, 4. Okay, same concept like we did with two-dimensional vectors. All right, and then the other one is OP. So O to P is 2 in the X direction, 1 in the Y direction. It doesn't go up there. So this is what you get, 0, 0, 4. And this concept is quite helpful because you will see that when we are talking about the distance, when you calculate the distance, this concept comes in very handy. Okay, you know that when you find the distance, you use Pythagoras, but here it's quite going to be straightforward because your I, your j is 0, 0, so the distance will be very easy for you to determine. So can you directly see that PQ, P to Q is equal to 0, 0, 4? Yes, you can see. Just look at that distance up there. What is that in I, J, and K form? In I, J, and K form is, well, taking out that 4, okay, because you know it's 0, 0, 1, because multiplying that by 4. So it's just 4K. Okay, so you have to get used to working with both notations, and if you are asked in vector form or in column vector form, then you give your answer in column vector form. If you're asked to give your answer in unit vector form or base vectors, then you give your answers in base vector form. Like this case is 4K, and then you have to draw a little line under the K when you write it down. So when you write it down in your book, right, this is going to be vector 4, and then you put a little line under that, okay, in order for you to indicate, right? So if you have let's say, just take this off. So if you have something like 2, 1, and 4, okay, then this is going to be 2i plus 1j, and there's no need to write that 1, plus 4k, for example, just to put it out there so you don't make any mistakes when you are writing or requested to write things in unit vector form. Okay, right, so let's continue. As I said, we have a lot of slides to go through. Multiplying by a scalar, now it's not that difficult. You multiply each component in the column vector by that scalar, 3 times the direction, okay, 3 times as long. Quantities which only have magnitude, such as distance, mass, and speed, they are called scalar quantities. But things that have got magnitude and direction, such as when you talk about velocity, force, acceleration, we are now talking about vector quantities. Okay, right. So what is velocity? Velocity is like speed, and then also the direction, okay, and stuff like that. When you multiply a vector by a scalar, you're just scaling that vector. So it's either you're making it small or big. That's all that you need to understand when you're dealing with scalar quantities. To multiply by a scalar, multiply the horizontal distance, the vertical distance, and also you know, by that scalar number. So, for example, you have got vector A here, twice A. Just multiply. It's just stretch that 2 times that. Okay. To divide by a scalar, then normally the scalar would be a fraction. All right, so you're gonna half that. So divide by a scalar, divide the horizontal distance by whatever that x value is, and the vertical distance whatever that is. Right, so half into that. So scalar quantity means, you know, you just half, make that vector smaller. Right, so let's come back to parallel vectors. Scalar multiplication generate new vectors, and these vectors are called parallel. They are parallel to the original vector. So 2 vectors are parallel if one is a scalar multiple of the other. Now this is a very important sentence, because you do come across the sentence sometimes and you will see I'll do something on ordinary level, a question that deals with scalar or vectors, right? And then you have to explain, give an example why, you know, what do you notice from the 2 vectors, and then you just give your simple answer as the 2 vectors are scalar multiples of the other, okay, because they are parallel. Right, so when you look at this 3, -2, 4, and you have 9, -6, 12, -12, 8, 16, you would see that here, if you take out, you know, 3 and -4, these are scalar quantities, okay, because 3 times 3, okay, can you see that, and 3 times that, and 3 times that gives you this value here. Well, if you look at this particular value, this particular vector, if you take out -4, you do get this other vectors you can see there. So these are parallel vectors. So let's look at an exercise. So in this particular exercise, you're supposed to find your value of x and y. So you've got unknowns here, but then you have to complete and look at the side that is completed. From the vectors, you have to form three equations. First, you see x is equal to h times 1. 6 is equal to minus 3h. This one is interesting because we actually can calculate the value of h, as I did. All right. So if h is equal to -2 and h is equal to x, therefore x is equal to -2. So that takes care of that. So now this other one will be 5h equals to y, but we know what h is. All right. So y equals to 5h. So we substitute that value of h there to get our value of y, which is equal to -10. Quite interesting problem. And then you'll be able to solve it. Okay, so let's look at another one. You've got vector AB is given as 2i minus 3j plus 6k. Vector CD is given as minus 4i plus 6j plus qk. So we have to find the value of q, given that AB and CD are parallel. So if they are parallel, so write them as column vectors. The other one is going to be obviously with a q there. Can you see that? Right, in order for us to find our k, now here's the thing, people are asking, does it matter where you put the k? Not really. So I put the k on this side, I could have done it on that side. So we're going to go back to our first way of solving that, okay? So we need to determine the value of k. So it's going to be 2 times k equals to -4. I could easily have used -3 times k equal to 6. I can still get my value of k, which is -2. Okay, as I'm indicating. So bottom line, I got the value of k now. It's just that if I take the k on the other side, it might become a fraction, but it's not what I'm looking for. I'm looking for the value of k, of q. Right, so now that you know what k is, so you're going to say 6k equals to q, but k is -2, gives you -12. So the question now remains, what if you put your k on the other side, on the -4, 6, and q side? It'll also work, right? So you have here 2 equals to -4k. That still gives you k as a half, -1/2, but it doesn't matter, all right? It will work. So now you say that 6k is equal to q, 6 times qk, this one here. 6k times q, but we know what k is. Substituting k in there, well, you get q equals to -12. Well, you still get to the same answer. Bottom line is you have to calculate the value of q. We use that concept of parallel vectors. The magnitude of a three-dimensional vector, well, the same way we calculated the magnitude of a two-dimensional vector, we use Pythagoras' theorem. So if we know what the point is, okay, and we can just take all those points, so it's 2, 1, 4, you just square it. All right, now it's perhaps a very interesting particular point here that I want you to have a look at in order for you to see how one gets to that. Okay, but as I said, if you have a three-dimensional vector, you simply take each component and you square it and you take the square root of that. But first, what I did here is I calculated OP, and OP in two-dimensional vector will be that 2 squared plus 1 squared, which gives you 5. Okay, so if OP is equal to 5, as I'm bringing it back here, OP is equal to 5, then if I had to find a vertical one from O to Q, it has to be this 5 that I calculated, okay? Because you're looking for a OP. An OP squared is 5 from my previous answer. Now I want to find the other distance from P to Q. Well, P to Q is nothing but 4. So it's 5 plus 4 squared, which is 21. Right? So O to Q will be the square root of 21. But again, you don't have to worry too much about developing a formula. You just have to say that you look at every component and you square it. Okay, so this is what I want you to have a look at. So you have got vector OP is x, y, z. Its magnitude will be the square root of x squared plus y squared plus z squared. Remember, you should have the squares of this should give you positive values, okay? Otherwise, the magnitude will not exist if you have a negative thing under the square root. So be careful with your substitution. All right. So what I simply mean by that is sometimes people they tend to make mistakes. So they will have things like this under the square root, and then they could get I don't know, something like that, which does not exist. So it's that -2 should be squared, right? So that you know that the answer exists, because magnitude has to be positive. So sometimes it's just the way in which you are recording this stuff down, so that make sure you don't make those mistakes again. All right, they are quite common. We see that a lot, and avoid to make these type of mistakes and focus on. Sometimes when you use this magnitude formula, you don't even need to put the negatives there, because you know that the answer should be a positive value anyway. Okay, right. So the magnitude of OP, is written with that the bars there, and then the arrow on top there if it's capital letters. Otherwise, if you represent it by a small letter B, then put a line under that small letter B, put it in bars. All right, so we have got some questions. What is the magnitude of this? So it's going to be very easy. This one here, 3 squared plus 4 squared plus 1 squared, square root of 26. Well, this one here, well, this is very interesting. I'll let it maybe sink in. 0 squared plus 4 squared plus 0 squared. The answer will be 4, because remember, this is now only 4 units in the y direction. So that distance can be measured. Do you follow what I mean? All right, because it doesn't go up, it doesn't go across, to the left, to the right. It's just that it's 90 degrees. All of these are rectangular faces, so it should be 4 units. No need here to use the formula. If you have 0 zeros in the other, the I, the K 0, then you can find the magnitude easily. Right. Well, this one here, again, that concept where I said be very careful. So you put the negatives in brackets, or you can take them out if you want to. So how do you make a unit vector? Not all unit vectors run parallel to the x-axis. That is one of the things I mentioned right in the beginning when I say how you make a unit vector. And I said, well, we have a fraction is coming a little bit of a tricky situation. To do this quite easily, you just divide the given vector by its own length. So we have to use the length in order to create unit vectors. So let's look at, we have this vector here, 3i plus 4j. So 3i plus 4j, so it's 1, 2, 3, I direction, 1, 2, 3 in the y direction, plus 4j. So the same applies here. It's the same vector. So when you use Pythagoras theorem, you find that the magnitude of vector A is equal to 5 units. Okay, so that 5 units there, if you have to look at it, and here we bring in something really interesting again. Okay, we say A cap, something like a circumflex on top of that. All right, so whatever it is in the I direction, because that 5 says we have to go 3 in the I direction and 4 units in the j direction. Okay, so A with little circumflex over 8. So it's like 5 of these little things. Okay, this is the magnitude of that. So it has to be 3 over 5 plus 4 over 5. So where's the 5 coming from? So the 5 is basically your, yes, is your distance. So you will be saying 1 over 5 times each of the components in order for you to be able to find, to create a unit vector. Okay. Let's look at a few questions and then you can get an idea. So, so what I'm saying is that to get the unit vector A hat A from any vector A, all you need to do is take the vector A and divide each of the component by the magnitude of that vector. Okay, A hat equals to A upon the magnitude of A. Let's look at it. So you have got, let's say we take a 3-dimensional vector, so 8i plus j minus 4k. So we need to find the unit vector. So first you find, let that be vector A, no problem. Okay, so you need to find the magnitude. Magnitude is easily used by Pythagoras' theorem. And now each one of those components has to be multiplied by 1 over 9, 1 over 9, 1 over 9. So you can go ahead and distribute that 9. So it's 8 over 9i plus 1 over 9j minus 4 over 9k. Okay, so the question was given in base vector form or unit vector form, so we have to leave it in unit vector form. Or if it's column vector, you take the 1 over 9 out and then say a hat equals to that 8, 1, negative 4. All right, so we have got a question here. So when we look at these questions, we have to be a bit considerate, a bit careful. Okay, so we also find the coordinates of r, where the magnitude of OR is equal to 6, and OR is in the direction of 2i minus 3j plus 6k. So what is it that we know? So we know that the magnitude is equal to 7. So we know this 2 squared plus 3 squared plus 6 squared over the square root is giving you the 7. We know this. So the unit vector is in the same direction. So OR is in the same direction. Okay, I think it's supposed to equal to 6 there. It's just a little mistake there. All right, so we then take if you look at 2 squared plus 3 squared, you see I put here, I didn't put it minus 3 in brackets all squared. I know that if I just take 3 squared, this is the same as minus 3 in brackets squared. So you get 7. So that's the magnitude of this vector. But we know that OR, which is what we need to find, all right, we need to find the coordinates of R, such that OR is equal to 6, and OR, vector OR is in the same direction. So there is that parallelism there. Same direction. So that 1 over 7 becomes now something I should multiply every component with in order for me to find the final answer. Need this vector 2, 7i minus 3, 7j plus 6, 7k has a magnitude of 1. So if O to R, the absolute value or the modulus of or the distance of OR is equal to 6, okay, then OR should be 6 times more than that magnitude, that vector with a magnitude of 1. 6 times more. So 6 therefore have to be multiplied with everything there. So you first have to find the magnitude, okay, and then we are trying to, well, you can use the formula and you will see exactly what I mean when I get to that part. Bottom line is they say find the coordinates, and then you don't write in terms of I, J, and K. Write this 12, 7, minus 18, 7, 36, 7. So we have another one here. Find the coordinates of A. If the distance of O to A, vector OA is equal to 5 units in the same direction as OB, where B is the point, 2, negative 1, 4. So maybe you can pause and try to see if you can determine what to do. So first, we know what OB is. 2i minus j plus 4k can also be written. So O to B then, now find the magnitude, the square root of 21. The unit vector, the direction OB, to make OB a unit vector. And then once I get that, then I will be multiplying that by 5 in order to find point OA, right? So unit vector means you have to multiply each component there with that square root of 21. Now this is a unit vector now. So OA will be 5 times that, okay? 5 times that unit vector. So you multiply everything by 5. So 5 times 2 is 10, 5 times 1 is 5, 5 times 4 is 20. So what are the coordinates of A? Coordinates of A is nothing but 10 root 21, negative 5 root 21, 20 root 21. So similar questions, just ask a little bit differently. So make sure that you can get that. Here this question is interesting. They say find the vector C. We need to find a vector. We are given the magnitude and the unit vector of C hat. Okay. Right, so let me bring the formula in again. C hat equals to vector C upon the distance of that vector. So we need to find C. So it's like mix something the subject formula. So it's like you are multiplying, okay, that C hat with the absolute distance in order for us to find vector C. So we know that the distance is 24. So I'll be multiplying that 24 with everything on that side. And that's what you see in order for me to get the vector C there. So it's just going to be 24 times each one of those components there. Okay, right, now they want me to find the vector C. So now the vector C is 16i minus 16j minus 8k, okay, which you can also write in vector form. If they ask you in column vector form, you could have written it like this. But since the question is dealing with questions in terms of unit vectors, I will leave it like that, or base vectors. Question 4, we have got OB is equal to that, OC is equal to that, OD is equal to that. Now look at the OD, you have 3i minus 4k, so there is no JE value, careful. And O is the origin, write down the coordinates of D. So what would be the coordinates of D is 3, 0, negative 4. You agree? All right. Coordinates of D would be, well, 3, 0, negative 4. So if a question starts with column vectors, you end with column vectors. This question, you come across that. This is a kind of very important. I was repeating this. I kept on repeating and repeating and repeating it, so that you know what to do in the exams. If a question starts with base vector form, then you should leave your answer with base vector form. In this particular case, in the first part, you just want to find the coordinates of D, which is very straightforward. So I had then to only write from base vector form into column vector form, and then I know that there's a column vector form from position vector is the same as 3, 0, negative 4. Right, so CD, again, how do you find CD? You say OD, second position vector point, minus first position vector point. So you have to go and write each one. So OD is given to you as 3, 0, negative 4. Okay, or you can, because the questions are in base vector form, so 3 plus 0j minus 4k minus, since you are subtracting, please put the other stuff in brackets. All right, OC is given to you on top there. And then you just go ahead and you subtract and you change the sign. You should get to an answer of minus I plus j minus 7k. They say find the unit vector in the direction of OB, vector OB, in terms of I and j. So first we have to find, here's the distance, all right? Once you have the distance, then you make that a unit vector, okay? So 1 over 3 of that times each one of those components, well, that's going to give you the answer for that particular question. Right, this is an important concept, the midpoints of vectors. So I hope you pay attention to that. So if you have vector OA and if you have vector OB, so we want to find the midpoint of that. OA and OB are called position vectors because they start from the origin. They're tied to the origin. Then OM is the midpoint, right? So how do you find that midpoint? So O to M, to go from O to M, you have to go OA plus half of AB. This is a very important concept because we're looking at O to M. Okay? It's OA plus half of AB. Now this is going to assist you immensely. So say I give you a point AC and I want you to find point M, which is the midpoint of that. You see, this particular part we say OA, okay, and then half of AB. So in this particular question, the way you'll do it, you say OA plus half of AC. So whatever that OA is, that first point that is given to you, okay, plus half of what is connecting them. This concept is quite useful and it will assist you to find the particular values. So if I wanted to find OM and I have got something in terms of AB, so I have to go from O to A plus half of AB. So let's look at some questions that we can use. So relative to the origin, the position vectors of the points A, B, and C are given below. First, they say you must find AC. Now, AC is very interesting to find. So AC, you are saying OC minus OA, second position point minus first position point. No problem. You just substitute and then you calculate. Okay, so this gives you the value of AC. Now, the point M is the midpoint of AC. Find the unit vector in the direction of OM. So what is OM? OM is OA plus half of AC, like what I said before. Right, so let's clean this up. So OM then will be OA, which we know as 1, negative 3, 2, plus half of what we calculated before. That gives us OM. Now we have to find the unit vector. So in order to find a unit vector, first we have to find the magnitude. And once we have the magnitude, we are going to multiply the magnitude with each component there. All right, so it's given in terms of column vectors. So you can go ahead and leave the 1 over the root 5. It's always 1 over there. times each one of those components. You can go ahead if you want to and write down everything as it is. Maybe you will not be able to see that part, but what this little part means here. So you have got your 2. So you just now multiply it with the root 5, and you have got your -1 root 5, and the last point is the 0 root 5. Well, 0 divided by root 5 will just give you 0 anyway. Or ideally you can leave it like this with the scalar quantity outside. Okay, so we have got revision exercises as we get closer and closer to the end of the slides. So you have got a triangular prism, as you can see, and OD is 6i, OC is HJ, and OA is 10K. Now I just complete the values, and I hope you can do the same. Okay, right. So that takes care of write-down coordinates of the vertices, looking at the information that I'm given. That's how it would look. Now, if you were to look at my diagram and I bring it back here, they say find the vectors DC, DE, DA, DB, EB, DC, DC, the vector D to C. Right? That vector is, remember, to go from D to C is the same as going from D to O and then plus OC, or DC would be second position point minus first one. Okay, right? You can get to the answer. DE again, well, from D to E, well, you simply go up 10 units. Is it not so? 10K. DA, well, you can go ahead and say, you know, D to A. If you look at D to A, you go DO and OA. That's the direction you sort of travel. So you're going against this minus 6i plus 10K. Okay. And DB, well, D to B, again, look at D to B. So you are here, you want to go all the way there. So you're going in this direction here. So D to B, all right. It's DC. We already know what DC is from our previous answer. Plus CB. Now CB is the same as 10K. And EB, well, EB should be the same as DC, which we already calculated. Okay, so that should take care of that. They say M is the midpoint on DC. So wherever DC is, M is the midpoint, as you can see. And N is the midpoint on EB. What is the position vector of M to N? Well, that should be straightforward. So to go from M to N. Again, remember what I said, what I did with the previous question. So to the position vector of OM, or you're looking for the position vector of M, of vectors M and N. That is OM, which we know OM, going from O to M, that's supposed to be OD plus half of whatever that DC is, all right? So we can find that it's 6i plus a half of DC, which we already know. So that gives you, if you clean it up, you get just 3i plus 4j. That's OM, right? So if you had to find ON, so ON, well, you can go OD plus TE plus EN, or you can find other ways to get to that. But we know what OD is. O to D is 6i, D to E is 10K, all right? And then EB is going to be half of, right? EN will be half of EB. EB is the same as DC. Bottom line is you get to ON being that 3i plus 4j plus 10K. This was what this particular question wanted you to find. So it's like you're starting at a certain point. How do you go from this point in terms of the directions? And you use those base vectors. Right. So show that DN. So we have got, where's my D? D to N is the same distance as M to B. So it's like drawing those type of lines there. So DN, first of all, D to N is nothing but DE plus EN. So when I do DE, it's 10K plus EN, which I already know is half of what I had before. That's what I arrive at. Okay. Now let's look at MB. So M to B. M to B is MC plus CB. Okay. because we are looking for M to be. So it's that little distance there, which is half of DC, plus that 10K there. Half of DC from my previous work, I will arrive at the same answer. Then I've proven that these two are exactly equal. Right, question 2. You have got vector OA is equal to minus 5i plus 6j plus k. Vector OB is equal to 2i plus 4j plus 4k. OC is equal to that, where O is the origin. Find AC in terms of I, J, and K. So AC, which will be same as second position point, OC, all right, minus OA. Okay, OC minus OA, then you just go ahead and you please remember the bracket because we are subtracting, and then you should arrive at that answer as I did. Now they are saying the midpoints of AC and OB coincide. Now, let's say what is the midpoint M of AC? We know that the midpoint of AC will be OA plus half of AM. Okay, half of AC, sorry. So that goes from O to A plus AM. It's like O and you start at O, you end at M. But we know that it's going to midpoint, it's going to be OA, okay, plus half of AC. Right, we take that stuff that we have and we get to our answer. Then we have OM. Now let's look at OB. OB, the midpoint of OB would be a half. Okay, it's very easy. We know what OB is 2i plus 4j plus 4k. So the midpoints will just be equal to each one of those components, you know, being halved. And when you look at that, you see that they are equal. They coincide. Their displacements are exactly the same point. So that means they coincide. Okay. Right, so we have got a third question here. 4 points A, B, and C, D have position vectors, as you can see, relative to the origin. Find the vectors A, B, B, C, and B, D in the form of AI plus BJ plus CK. Again, AB would be OB minus OA. Okay. BC would be OC minus OB, and so on. So you just go ahead and then you substitute it correctly. And BC, again, as I said, OC minus OB. So you have to use that concept the same way we apply it in two-dimensional vectors. And the last one, BD, so OD minus OB. Well, that brings you to 12J minus K. I hope you can work it out and get to that answer as well. Then bring your vectors back. It says show that points A, B, and C are collinear points. AB is equal to that. BC is equal to that. And BC is twice AB. If you look at BC, it's 4i, 12j, 4k. So it's twice AB. So since BC is twice that, it means they have a common point B. All right? And they are therefore collinear. So A to B, which we have determined, is equal to I plus 6j minus 2k. BC is 4i plus 12j minus 4k. So obviously I want you to compare with what we have before. What is the ratio of AC, vector AC with AB with regard to vector AC? Well, vector AB, if we look at the absolute or the distance, is 2 root 11. And AC, now AC is interesting. You have to say OC minus OA, and then we get that answer is. And if we take the distance of that one, we get 6 root 11. Comparing the two, all right, cancelling the root 11s and simplify, give you 1:3. Very interesting. Again, have a look at these questions. And since I prepared the slide some time ago, I'll be looking at working out questions, examination type questions that involves with 3D stuff. All right, so this is the roof of a house, and they say the rectangle of OD of length 10 meters, as you can see, and OF is 8, all the way there, and the reach GH is 6 meters, symmetrically 3 meters above. So with the axis as shown, find the position vectors D, E, F, and H. Position vector of D, well, just 10I, because it goes that direction. Position vector of OE, that is O to E, so that will be 10I plus 8J. You agree? Doesn't go up. Position vector of F, well, that will be just 8J, because in that direction. H is very interesting. So now you know it's 10I, but now you must be careful because H is exactly halfway there, right? It has to be halfway, and it must be halfway, which is 4, because it says that it's 3 meters, it's symmetrically above the rectangle, and then you have got that distance which you're given as 3K. What is the length of each slant edge? The length of each slant edge. That means we have to find OG. So let's calculate OG, for example. Then OG is 2I plus 4J plus 3K. Okay. DH, in order for us to find DH, is OH minus OD. DH, well, we get DH and we clean it up, we get minus 2I plus 4J plus 3K, because it's due to H, so you can imagine, you know, the in terms of the direction, 2I. And then if you look at the EH, E to H, you have what? OH minus OE. When you clean this up, you get to that value there, minus 2I minus 4J plus 3K. So you use that, you know, position vector format in order for you to be able to determine. Okay. All right. How do we determine OG again? O to G, O to G. Remember, it's not exactly. And here's the thing about this one. You know, O to G is little distance here. And how do you get that little distance of 2 there? See, you have to look at DH. For example, OG is very easily to determine. You can see that, well, first of all, O to G, you have that 3, that it's 3 units above the rectangle, so that 3K is okay. And it's half of this distance here, which is half of 8, which is 4. But how do you get that to be 2? So maybe if I was to look at this maybe in a different perspective, okay? So suppose I am bringing this part in here, and you look at, we know that the whole distance from there to here should be 10, okay? But the 10 is a little bit out because it goes in, this distance is 6. So if you go all the way up to H, there's something a little bit in the air, right? So that whole, this is like OD, it should be 10. So you have something here and something here, a little distance there, right? So if I look at 6 plus those distances, should give me 10. All right, so that gives me 2x plus 6 is equal to 10. So that's 2x is equal to 6, 10 minus 6, which is 4. And my x will be 2. So that's how I know that the distance is 2 units, okay? Because it goes kind of in a little bit here, kind of in a little bit there as well. So G should be 2 units in the x direction, so to speak. Okay, so F to G again, you have to do each one of them and then you arrive at the answer. So F to G again, you OG minus OF, and then you get those values in order for you to be able. So the slant edges OG is equal to DH is equal to EH is equal to FG. All of these slant edges, because we are looking for the length of each one of them, and the length of each one of them should be exactly the same. Okay, so the length should equal to a root of 29, and you can actually calculate them all and you'll see you get